So today we're talking about work, kinetic energy, potential energy in springs. So really, spring energy is another kind of potential energy, really, right? Yesterday we dealt with gravitational potential energy, but today we're going to deal with spring potential energy and another formula. Okay, so basically this is the slide that is similar to the one that I showed you before with the pictures. You probably don't need to write it down. All I'm saying is that all springs follow the same law, whether they're the kind that you stretch out, the kind that you compress, or the kind that bounce up and down. Springs are springs. Okay, so Hooke's law, here's Robert Hooke, some sort of scientist dude from way back when. And Hooke's law relates the amount of force F that you exert on a spring to the distance x the spring is either stretched or compressed. And I think that sort of generally makes intuitive sense, right? As you stretch a spring, or it could be an elastic band, I guess, too. And as you stretch it, the amount of force, like that last little bit at the end, you need a lot of force, right? So as the thing gets stretched more and more, the amount of force that you need is more and more. I haven't told you what Hooke's law is. I'm just telling you what it's going to do. It's going to relate the amount of force that you exert on a spring to the distance that you stretch it or compress it. Now, normally we've done the lab at this point, but seeing as I'm flipping them, that's your graph that you're going to get on Monday. Ooh, a straight line graph. Shocking, right? So you can just draw like a quick sort of there. Right? It's a straight line. So your graph of force versus distance should look like this. So in other words, as the distance increases, the force will also increase, right? So from this straight line graph, you're going to get that the force is proportional to x. It's linearly proportional to, right? The greater the x, which is the distance, maybe it should be a d, I don't know. The greater the distance stretched or compressed, the greater the amount of force required to continue doing that. Right? And that takes you to the equation. I've sort of introduced you to this little process before, where you take a proportionality statement and you replace it with an equals, but then you got to put in this k value. What is it? Anybody remember? Constant of proportionality. It's the number that makes it work. Okay, examples include Newton's law, or Newton's universal gravitational constant, 6.67 times 10 to the minus 31. Planck's constant that you might have learned about in chemistry. Pi is a constant of proportionality. Pardon me? Something like that, right? There's all sorts of solubility constants. You guys done those in chemistry? Okay, so same idea, right? A constant that makes it work, depending on, like the solubility constant for, it's been a long time since I taught chemistry. Sodium is different than the solubility constant for, I don't know, lithium. Right? Okay, so the same is true here for spring constants. Every spring has its own constant. Yes. So Hooke's law says the force exerted upon a spring is directly proportional to the amount the spring is stretched or compressed, which is what we got from that graph. So what does that all mean? The k value, the constant k, is called the spring constant. And in this particular case of that graph, k is the slope of the line, which was 35 newtons per meter. So it's always, the spring constant is always the slope. Okay, in this case here, it's 35 is the constant, or the slope, and you express it in newtons per meter. You need 35 newtons of force for every meter of stretch. Dead or wouldn't connect? Which one was it there? Okay. You should have sample number 1 on that sheet, I think, don't you? I think you do, right? And I don't know why I've done it this way. I have no idea why I've interspersed the samples right in the middle there, but I guess I did this time. So, yeah, what are you going to do? When a 6 kilogram mass is attached to a vertical spring, the spring stretches or compresses a distance of 40 centimeters. Find the spring constant. Does this seem easy? Seems like a 1-mark question to me. Of course, I know what the answer is. I also know how big the box is, which probably means that there's only 1 or 2 steps in there. Okay, so what is the force? Because it's vertical, we got 6 kilograms. It's going to be times 9.8 for our gravity. 6 times 9.8, we need 58.8 newtons. Vertical spring. That's a good question, Joel. How do you know it's vertical? Right, so it's because it's hanging from something, it's a vertical one, right? The spring, or sitting on top of something, right? Yeah. So when you attach the 6 kilogram mass, the spring stretch is only 40 centimeters. Find the spring constant. So the force is 58. F equals kx. I don't know why they use x. I guess x is the distance. It could be kd, I guess, but maybe that would cause too many. I don't know, yeah. Maybe I should just call it kd. Go ahead.
Newtons per meter or Newton meter?
Newtons per meter. 58.8. And notice that it must be in you got to be able to convert centimeters to meters. So we're going to divide by 0.4 and you get 147 newtons per meter. So like I said, generally these spring constant numbers tend to be large numbers. But that's because of that 1 meter thing. So like really, like multiple choice question on a test, right? Like, yeah, pretty easy.
Do you mean it's rhythms?
You'd think that after enough times, have it. Although I think you do realize that, you just say it just in hopes. Yeah. Work and potential energy of springs. Okay, so now when you stretch, like if you put that 6 kilogram mass on a spring, right, and then took it off, the spring would bounce back, right? So you are actually putting potential energy in that spring. So here's kind of the theory, whether you want to write this down or not, it's up to you. Consider the amount of work you do on a spring with a 200 Newton per meter constant. Work equals force times distance. Force exerted is found by using Hooke's law, F equals kx. So this d right here and that x right there, which Blair is calling d, are kind of the same thing, right? And this f is that guy right there. Do you smell a formula derivation coming here? No, it's just paint. No? Okay, so we got spring energy is 1/2 kx squared. I don't know what's under here. Let's see. Okay, this defines what US is. Amount of potential energy stored in spring. So I guess, really, I've given you 2 formulas today, right? I've given you F equals kx, and I've given you potential spring energy 1/2 kx squared. But I've given the background, the theory. Here comes, how do you solve problems with this nonsense? Plug in numbers and do timesing. No. That's what happened to me. Don't cry. That and genetics. Why does this say sample 1? Did we not? Oh, it's sample 2 on yours? Some severe editing going on here. All right, sample 1. Oh, this looks easy. I only got a single box covering up the answer. If you do 24 joules of work in compressing a spring whose constant is 80 newtons per meter, how far is the spring compressed? So I'm solving for the letter X. How far, right? In Blair's world, it's a D. In Shelby's world, it's a D. If you do 24 joules of work in compressing a spring whose constant is 80 newtons per meter, how far is it compressed? US equals
1/2.
1/2 kx squared. Joules of work. The spring constant is 80 newtons per meter, so this is the K. Right? And the work is going to be the US, right? Because that work is transferred to spring energy. So 24 equals 1/2. Now it's 80, right? Now, I've used the 1/2, but I guess really, if you prefer US equals kx squared over 2, if you want that, if that makes more algebraic sense to you, that's good, because then that sort of forces the multiply, right? So multiply by 2, you're going to get 48 divided by 80. Take the square root. Do I need to show those steps, Joel?
No,
Okay. I'll show those steps for you if you want. I guess you could do this, would be better, right? 40x squared? Okay, fair enough. Never thought of it that way. .77? Oh, yeah, it's right there. What am I doing? Here's sample number 2. Now this one's a little trickier. So we got a spring. It's got a constant of 200 newtons per meter. It's been compressed 0.1 meters already. Okay? How much work must you do from this point to compress it to the 0.4 mark? So it's already got some potential energy, right? So the force doesn't start at 0. The force starts at some value greater than 0, right? So this is a little bit different. So again, the work done is the potential energy gained, right? Initial spring energy. HSE. Holy sorry, everybody. Potential spring energy, the initial spring energy is 1/2 kx squared. So 1/2 200 times 0.1 squared. It has 1 joule of stored energy to begin with. Okay? It has 1 joule of energy to begin with, Joel, because it's already been compressed. Yeah. Oh, well, why didn't you say so?
1 joule? Yeah.
1 joule. The final, how much work must you do to get it to the 0.4 mark? So how much does it have at the 0.4 mark? 1/2 kx squared, 1/2 200 times 0.4. It has 16 joules. So what does that tell you? If you started with a joule and you did work, and now you've got 16 joules, how much work did you do? Are we done here?
No.
It feels like we should be done. Oh yeah, a little note here. You should probably write this down because people want to do this. They think, well, can I just go 0.4 minus 0.1 and get 0.3 and then take that and substitute it in there for the x, for the d. Okay? You can't, yes. So the 0.3 is delta x, not the total compression. So that's the reason I picked this sample. Don't do that. Although maybe this would be one of those cases where if I never showed you that, then you would never even think of doing that. I don't know. Do it this way. Is there one more to do?
Yeah.
Okay. Here's the part that Hannah's been dreading. where it gets hard.
Are these more notes?
This goes back to the note side, yeah.
Ah,
Sorry.
when you go.
Work, potential energy, and kinetic energy in mass spring interaction. So in other words, pardon me? We're kind of talking about momentum. We're talking about objects hitting springs and slowing down. Or I guess being slingshot away and speeding up, right? And so work done. So now this is similar to the objects that went up in the air and are gaining potential energy and losing kinetic energy, right? So it's the same kind of deal. When you run into a spring, you lose kinetic energy, but the spring gains potential energy, doesn't it? Right? So this is sort of analogous to that. Work, potential energy, and kinetic energy in mass spring interactions. Collisions. No two-dimensional ones.
Oh my god.
I don't want any part of that. That even hurts my head, well, just watching. Maybe that might be the reason not to do driver's ed, just because of my head. I have to wear a helmet.
I was gonna say, would they let it concussed?
I don't know.
Exit concussed?
Mrs. Jordan said that one kid.
Okay, better get this done. Consider a mass colliding with a spring as shown. Let's see the picture here. There it is there. Okay, so this is my lame attempt at, here's the mass here, right? And it's just encountering this squiggle line right here that I'm going to draw in blue is the spring. Whatever, right? That's the spring. Yeah.
Wow.
Van Gogh.
That's how Van Gogh would draw it.
What's that stripy line?
That's just a solid. Usually they put the stripy line that indicates that it's fixed, it's in place, it's not movable. Yeah, it's a wall. Usually that stripy line means that. So before the collision, all the energy is kinetic, right? The total energy is all kinetic because the spring hasn't done any compressing yet, right? It's just touched it. Yes, Joel? There used to be, long time ago. My predecessor, Mr. Sorin, who was the physics teacher, Mr. Sorin, not syringe, Mr. Sorin. He actually was, I think, hired as a drafting teacher and then ended up teaching physics because it kind of ties into engineering. So. Sorin. Now, what about during collision? During collision, the kinetic energy of the mass decreases as it slows down, but as it slows down, it's doing work to compress the spring. Where does that energy go, Hannah? Hannah, please put it away. Here's the hard part today. Seriously. Okay? Focus. 5 minutes. So the kinetic energy decreases as it does work to compress the spring. And as always, this energy must be conserved. So the total energy, ET, is the kinetic energy plus the potential energy. And when you break those down, it's mv squared over 2. And I don't know why I did that. mv squared over 2 plus 1/2 kx squared. Or I guess if you want, kx squared over 2. Right? Now that I think of it, this is virtually the same as potential energy up and down, right? Good? Before collision, all the energy is kinetic. During the collision, the kinetic energy of the mass decreases as it does work. So what's happening here? What happens when it's all done? When the spring is all compressed, all of the energy is transferred to the spring, and the kinetic energy is 0. So that is similar to the object doing what? Getting to its peak, is it not? Where all the potential energy is, right? Right? So at the end of the collision, all of the energy is transferred to the spring, and the kinetic energy is 0. In other words, the initial kinetic energy is equal to the final potential energy.
Does that say
USF, final spring energy. And it's all in one slide, so it can't be that hard. A 5 kilogram mass moving at 5 meters per second strikes a spring bumper, like in the old bumper cars. Having a spring constant of 50 newtons per meter, find the kinetic energy of the mass before collision. How far will the spring compress? And the weird one, kinetic energy of the mass after compression of the spring, only 0.8. So halfway, or some portion of, right? So find the kinetic energy of the mass before collision. Kinetic energy is mv squared over 2. So that's easy. How about how far does the spring compress? Well, what happens to the 62.5 joules of kinetic energy? It's converted to work, which is converted to spring energy. So it's, right? I mean, I guess here I wrote that, but I mean, I guess that's the same as US, right? All of the spring energy, that's 62.5, is converted. And US equals 1/2 kx squared. Yeah, I don't like that, how that's.
So 50 is K?
50 is the K. 1.58 meters. That's a long way. That's a lot of compression. Over 1.5 meters, right? Springs don't compress that much. So that means that most springs have significantly greater spring constants than 50. Yeah. I think these were old PowerPoint slides that I couldn't do practice very well on. What if it was a slinky? Slinkies don't compress. Slinkies are the kind you stretch. What's the kinetic energy of the mass after the compression of the spring? 0.8. So how are we going to do this? If we had 62.5 joules to begin with, at some point along the way, I still need to have a total of 62.5, and some of that is kinetic, some of that is going to be potential. So I need to figure out how much potential I have, and then the difference is going to be the kinetic, is it not? Right? Did that sort of blow you away there a little bit? If I go ET is equal to EK plus US, right? I know what the total is. It's my 62.5. I can find the US because I got the distance, and then I'm just going to subtract, right? ET is equal to EK plus U. Total is 62.5. How much kinetic energy? US is 1/2 kx squared. These are easy. Right, so you'd have 46.5. I don't even know what the mass is. 5. 5b squared over 2, right? So b is going to be 2 times 46.5 divided by 5, and you got to square root that. You tell me, Dan. I don't want to. Seems slow, right? 4.3? Does that seem about right? How fast is it going to start? 5, right? Yeah. When does it lose most of its speed? The start or at the end? The end. At the end when the force gets greater, right? Yeah. Right? Because you're dividing by 5? No? I'll do it another? Is that good or bad, Dan, do you think?
Bad.
Yeah?
Yeah.
Well, it's good to be exposed to multiple ways, don't you think? Of doing things? See the connections? Sometimes I do that on purpose, sometimes I do it by accident. Sometimes I just do it by habit, I guess. I don't know. How did you think I was going to do that? Oh. Which is? Yeah? Divided by 4. By 5, right? And yet there's some, I guess some people might prefer this, Dan. 46.5. 5 divided by 2 is 2.5 d squared, right? Yeah. I mean, it's all really the same, right? Yeah. Okay, time for me to be quiet.